Hello, I will be setting up an XPSWM model, or actually an XPSTORM model, um, for a proposed apartment building development consisting of two buildings, a storm sewer system connected to an existing city storm sewer. The the storm sewer is designed as a dual system, meaning that there are going to be pipes underground and overflows over the surface. There will also be surface storage and underground storage. So what I've done so far is I opened up a blank file, going to new blank job, named it data.xp, and that's where I'm at right now. So first thing I'm going to do is I have been provided with a CAD file with a storm sewer system and the catchment areas. So first thing I will do is I will import that file as the background for the model. So go to CAD Files, load CAD. This is the name of the file that we'll be using. There it is. So what it is this is basically the extent of the development, where those purple lines are. Those lines are the catchment areas, and the green lines is the storm sewer system. So first thing we will do is we will map out the storm sewer exactly the way it is shown in the background CAD file. So we'll zoom in a bit and we'll start building the system. These are the catch basins. You can see that some manholes are CB manhole combinations, some are just regular manholes. There's another catch basin, the square one. There's a connection for the building itself. There's the other building with the connection at this location. Catch basin, manhole, catch basin, and so on. There's actually going to be an underground storage at this location, so we'll have to figure out how to model that. And there will be an orifice at the downstream end of this manhole that will control the two upstream areas corresponding to the two buildings. And then together with some uncontrolled flow, the sewer will connect to an existing storm sewer system, which is actually not shown here, but it's running perpendicular to the connection, so it's running along here. But we'll be ending the model at this point, so we don't really need to see the existing storm sewer on this drawing. So we'll start tracing out the storm sewer system. So first we want to make sure that we select the hydraulics mode, clicking on HDR at the top, and here we have nodes, so we'll click on the nodes and then basically just start clicking wherever there is a structure. At this point we're just going to create a node everywhere where there's a structure, no matter if it's a CB or a CB manhole or manhole, and later we will change them such that the catch basins and the catch basin manholes will become storage nodes, meaning that at those points we will specify the available underground and surface storage. The manholes will not have a storage associated with them, so just the CB manholes, and then we'll have to set up a underground storage at this location, which it's going to be some kind of an underground stormwater tank. Okay, so we already selected the node icon, and we can just start clicking wherever the nodes are until we get the whole system mapped out. basically have all the structures laid out. What I'm going to do next is for the roof connections, I will also set that up as a node. So we'll put one node here and one node where the other building will connect. Then also we'll set up the outfall, which is set up as a regular node, and later we'll change it into an outfall node. Currently they're all set as regular nodes, but we'll adjust them later. Another thing I'm going to do is for all the blind connections, meaning any connection where a catch basin connects to the main pipe, not through a manhole but directly to the pipe, I'll set those up as nodes because it makes the system more realistic, and we can then set up the inverts at that junction directly. So we'll again pick the node icon, and where there's a blind connection we'll put a node. Oops. Okay, now I made a little mistake here. I clicked the node by mistake, so I will right click on it and go delete that node. What I wanted to do is I wanted to zoom out of the system a bit so I can find the other blind connections. Okay, so I see there's one here. Nothing there. Let's see at the back here. I don't see any blind connections. If we miss any, you can always set them up later. Right. So the next thing I will do is I have a CAD file that tells me what these catch basin and catch basin manholes have actually been named in the design itself. So I will change the names of the nodes to the actual name that corresponds to the design drawing. So for example, this node, I will click on it and right click and go to properties, and instead of node 19, I know that this one is called CB5. This one, again, click on it, right click, properties. This one is called CBMH22, standing for CB manhole 22. This one here, this one here is called manhole 21, I believe. Okay, and I will change all the other ones as well. Now while I'm doing this, I'm going to turn off this something called snap mode. It just makes it easier to align nodes to the background CAD file. If the snap is on, it doesn't let you put it in the exact location where you want that node to be. If you're very particular and you want to have those nodes at the exact location of the structure, so I'll turn again, go into Tools, Snap Mode, and click on it and to turn it off. So I have the structure names all changed to match the design drawings. For the CB manholes, I call them the same as the drawings. Then we have a number of storm plugs for the building, so I just named those storm plug 2 and storm plug 1 for the other building. And what remains is the blind connections. which are not named on the drawings, but I'm going to name them according to the CB that's draining into that location. So so for CB4, I'm going to call this for example, blind connection 4. And same, I will label the other blind connections. I think there are a total of 3 of them. There's a blind connection here. Eight. And I think there's another one somewhere else. I'm going to name that one accordingly as well. This is how the model looks now. Zoom in a bit. We have all the structures set up, and next thing we will do is we'll add the pipes between the structures. There's a link icon, a multi-link, and a bridge, which we will not be using. We will be using for now. I'm going to set it up as just single links, and later on we may change some of them to multi-links, meaning that there's going to be pipe flow as well as overland flow. For example, between these two structures, we will have flow going through the pipe, and then these catchment areas, what's happening is the water will pond on those CBs, and then it might spill to the next area, and so on. So we'll set those up later as multiple links for the pipe and for the spill. But for the time being, I'm just going to select link and start connecting the structures. Just click on the structure, the upstream structure. Click on the downstream, and hit escape. Upstream, downstream, escape. Upstream, downstream, escape. Or I think you may be able to go 1, 2, next, escape, and it sets it up so you don't have to do each pipe individually. We'll do the same thing for this branch here. 1, 2, 3, 4, 5, escape. Go for this branch. Escape. And so on. A couple of items here. The snap tool toggle I showed before by going to tool snap mode. There's actually an icon up here where you can turn on and off the snap. I'm going to leave it off as before. And one more thing I wanted to show is the links that are now labeled arbitrarily or in order of drawing those in. They're kind of irrelevant to what we are doing, so we're going to turn those off by going under the links layer, and where it says labels, I'm going to turn that off because we don't need to see those values. we'll keep the structure IDs because they correspond to the design, so they're useful. Next thing I'm going to do is I will delineate the catchment areas contributing to individual structures. And so, for example, if I zoom in here, this catchment drains to CB54, this one to CB manhole 11, this building drains to storm plug 1, and so on. So to do that, we will skip to the runoff mode by clicking on runoff. We will select catchment under the layers, and by doing that, this little icon here should sort of light up. It was gray before, now it's kind of bluish and brown. So now it can be selected, and then we'll specify each corner of the catchment area. And hit escape. Sorry, you have to double click. Okay, and then the area sort of colors itself in. So at the end you have to double click, and that sort of closes the polygon. So for this one we'll go here, there. So now it's actually better to pick the snap on, because if the corners of the catchment areas should match the corner of the adjacent area, then it's better to have the snap, and that way the same point is selected. Otherwise you will have to go to each node, each corner of the catchment area, right click on it and pick weld vertices. That way the two kind of get welded together, and then if you click on them, you can actually select, by selecting that node, it should change, it should pull up both catchments sort of at the same time, so that you don't have to adjust the two individual to match the single point. So we have the snap selected, so again we'll click on this polygon icon, and 1, 2, 3, and double click. Oh, sorry, here's a little bit of an irregular shape there, and now double click. Okay, and I'm hoping that when I draw the second one, that those corners will get sort of welded together because I picked the snap. Double click. Okay, and we'll check if that's actually happened or not. So if I go to the corner, right click, nothing's happening. Okay, so I had to left click on it, and then it is welded together, so that's a good thing. Oops. So in the same manner, I'm going to trace out all the remaining catchment areas, and if the drawing is in real coordinates, georeferenced, then eventually the program will calculate the size of each catchment area without the user having to specify what the area is, and that's a very useful feature. And double click. the cursor actually turns into a little cross where it finds the previously drawn corner of the catchment area, so you know that you're hitting the same point. Okay, I'll do this with all the remaining catchments. Okay, so I'm still drawing these catchment areas. One thing I'm going to do is the fill color is kind of dark, and it's covering whatever's underneath it, so I'm going to change that a little bit, and that can be done by right clicking on the catchments, going to properties, and I'm just going to set the opacity lower. Let's see if that works. Yeah, so it's made it a little bit lighter, and now it's a little bit easier to see what's underneath it. So the catchments are set up, and next thing we need to do is tell the program which catchment drains to which structure. So to do that, we'll zoom in a bit so it's easier to work with, and we know that this catchment is draining to this catch basin, so we just click on this dark green square that's sort of the centroid of the catchment, and click and drag the line and release it at that structure. Let go, and where it says drain catchment as, pick subcatchment 1. If there were more than one catchments draining to a structure, then we would pick 1, then 2 for the second one, 3, 4, and 5 if there were 5 of them. But here there's just 1, so we'll just pick catchment 1. Okay, we'll go to the next one. Click on the arrow, click on the catchment, click on the green square, and release the mouse at this structure. Okay, this one drains to the CB manhole. And do that for all the remaining catchments. Release catchment 1. This one, again, click on the drawing, click and hold the mouse on the green square, and drag that to this structure. Release, drain catchment, subcatchment 1, and so on. Okay, so we have the catchments set up. Basically, each catchment has a connection to a structure. That's shown by this dotted or dashed black line. Each catchment goes to a structure. Now, there's one important thing to do in order not to get an error when we run this, and that is any structure that's not receiving runoff should be removed from the runoff mode. So, for example, the CB5 is getting runoff from this catchment, and so is this CB manhole 22. But when we get to this point, this blind connection and this manhole are not getting any runoff directly from a catchment. So what we have to do is, so we're still in the runoff mode, click on that structure and go to the left here and click the minus sign which says remove object from mode, and by clicking that it turns into a square and it's no longer part of the runoff mode. So for all of these that are not receiving direct runoff, you have to remove them from the runoff mode. So this one is getting runoff. This one is, so okay, here's a blind connection that's not getting runoff. So we take that blind connection out. The CB is getting runoff. Okay, here's a bunch of them. So this manhole is not. So remove it. This manhole. This one. This one. And this one is okay because this CB is getting runoff from catchment 7. And do that with all the other structures. So this one is getting runoff. So is that one. This one's not. So remove it. And so on. The next thing I will do is start populating some of the structures that we have in the model, and I will start with the catch basins and catch basin manholes, and we'll enter the invert elevation, the storage that's available at each of these nodes, and the so-called spill elevation. I'm going to turn off the catchment layer for a moment, for now, just so we can see it a little bit better. We want to be in the hydraulics mode so that the sewer system is visible, and we will start up here. So the way to do this is let's start at CB1. First thing we want to do is right click on it, edit data, and make this into a storage node, which means it will allow us to model the actual storage that's going to be available at that catch basin, meaning storage within the catch basin itself and on the surface directly above the catch basin, because we will actually have about up to 0.3 meters of ponding before the system spills to the adjacent catchment area. So we will make this into a storage node, and it'll pop up with another dialog box. We will measure the depth from the invert, and then select storage method. We'll select stepwise linear. Okay. And another dialog box pops up, and what we want to do is we want to indicate the depth to the invert, so that's going to be 0. So from the invert to the invert, that's 0. Then the depth to the rim, and the third one will be the depth to the spill point. So I have a table of storage curves which were provided to me by the designer based on the grading plan and the elevations. So for example, catch basin 1, we'll start with 0.00, and the storage area in hectares is going to be basically the area of the catch basin structure. So our catch basins are 600 millimeters by 600, so that's 0.6 times 0.6, and it has to be in hectares, so we have to divide that by 10,000. Okay, small number, could probably make it 0. So regardless, we'll put in the actual number. So that's 1, 2, 3, 4 zeros, 36. We'll insert another one. So it's going to be the top of the catch basin, which is 1.5 meters above the invert, and there the storage surface area is also just the area of the catch basin. So 0.00036, and add one more, and this is the top of the ponding. So it's 1.5 meters to the rim, and then 0.3 meters of ponding, so 1.8, and there the surface area that was given to me is 53 square meters. So 53 divided by 10,000 is 0.0053, and that gives the linear storage relationship for that catch basin. So we can click OK. Leave this as is for now. OK again, and here we will fill in the invert elevation for that catch basin, which is 177.25, and the spill crest elevation, which is the maximum ponding elevation at the 1.8 meter depth that we just entered, and so that's going to be 179.05. We'll leave everything else as is, and we'll return back to it later. Okay, so then we'll proceed to catch basin 9. Edit, and here we can actually put in the invert elevation first. It doesn't matter which order we do this in, but the invert is at 177.25. The spill elevation is at 179.05. Make this into a storage node. Stepwise linear method. And here again we'll put in 0 at 0.00036. Again, we have 1.5 meter depth to the rim, so 1.5, 0.00036, and 1.8 meters to the spill, and here we have 371 square meters, so that gives us 0.0371 hectares. Click OK, OK, and OK, and that sets up CB9. We'll do one more together. So this is CB manhole 8. The invert elevation is 176.63. The spill elevation is 179. Make this into a storage node. Stepwise linear. Now this is a CB manhole, so it's a little bit smaller in inside area. It's 0.31 square meters, so that's going to be 0.000031. The depth to the rim is 2.12. And the depth to the maximum ponding level is 2.37. It's 372 square meters, so it will be 0.0372 hectares. Okay, 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 and now we'll do the same thing to the rest of the CBs and CB manholes. One more thing for the storage node. When we click on it, I'm going to leave the ponding as none. That does not mean that it's not allowed to pond to the spill crest elevation. What that means is that it's not going to pond beyond that elevation. We can come back to this and adjust it if needed, if we get an error later. But that's the reason why I'm not setting it as allowed, even though there is ponding, simply because it's not allowed to pond beyond this spill crest elevation. So we'll leave it as none for the time being. Okay. Another thing we're going to do with the junction nodes, with the junctions, is we're going to set the inverts and the top elevation for the manholes that are not storage nodes. So we'll start here at manhole 7, and again I have the inverts listed here from the design drawing. So manhole 7 invert is 176.27, and the spill crest here, what we're going to put in is the actual top of the lid elevation or the rim elevation. So the ground elevation, so that is 178.89, and we're going to leave the rest as is for now. Okay, for the storm plugs for the building, it's a little tricky. So for now, what we're going to do is put in the actual invert elevation. So this is building A2, so the invert elevation here is 176.59, and for the spill crest, it is kind of a dummy node. There's no manhole at this point, it's just a connection from the building. We're just going to specify the ground elevation at that point. That's 179.50. Alright, and another kind of dummy node are the blind connections, and there again we're going to put in the invert, and that is the invert of the main pipe, not the invert of the pipe coming in, because the main pipe is lower than that blind connection. So the invert elevation I have calculated based on the inverts at the upstream manhole and the downstream manhole. So for blind connection 8, the invert of the main pipe is 175.97, and I estimated the ground elevation at that point. Again, there's no manhole because that's a blind connection, so the ground elevation at that point is 179.10. Okay, so on this branch, that's it for manholes and plugs and blind connections. We're going to move to this branch down here. These are storage nodes, which we already set. Another storage node, and here's a manhole, so we'll set that one, manhole 9. The actual invert elevation is 176.10, and the top ground elevation is 179.65. Okay, then we move. I'm going to go to manhole 3. So the actual invert elevation at manhole 3 is 175.51. The ground elevation is 179.15. And we're going to do this for all the remaining manholes, blind connections, and storm plugs at the building. For the outfall, I'm going to set the invert elevation for now as the downstream invert of this pipe, not of the main sewer. So the downstream elevation of this pipe, which is 174.79, and the spill crest, I believe it's a blind connection, so that's going to be just the ground elevation at that point, which is 178.50. And I'll double check this if if they're proposing a manhole, then we'll set the actual ground elevation, but I think it is a blind connection. And here, so we'll select outfall, and for now I'm going to leave it as free outfall, and we might actually come back and change this later because we have a stage storage curve or stage discharge curve at that point, which we're going to set later, but for now we'll just leave it as type 1. Okay, we're going to start entering the pipe data, and there's a handy tool here under tools, calculate conduit lengths. So we're going to use that, and it should calculate the right length based on the background CAD file, which would be in real coordinates. So by doing that, it will ask us all or selected, so we want to do all, calculate, and now it shows that the old length that was in the model was all set to 10 meters, sort of like a default value, and these are the new calculated values. So we click OK, and then, for example, if I go to this pipe, right click it, go edit data. Now I know it's going to be a circular pipe, so I pick circular, and it has the length in it, so 14.13 meters. So when I look at my table here from the design drawings, I see it's 14.12 on the design drawing, so we're close enough. So we'll leave that as is. What we are going to change is the roughness. We'll put in 0.013. We'll put in the upstream invert elevation 177.14, the downstream invert 177.00, and the diameter, which is in meters here, so it's a 250 millimeter pipe, so 0.250, and click OK. And we're going to go through all the pipes one by one. There probably is an easier way by using the XP tables. So maybe we'll figure out how to do that after we set a few pipes manually, so that we have a check. So I'm going to start here at this end. Pick this pipe, right click, edit data, circular pipe, and we already have the length populated. So look at my table here, CB5 to CB manhole 22. In my table it's 3575, so again we're close enough. We'll change this to 13. Upstream invert is 177.67. Downstream invert 177.27. Sorry, 27. And the diameter is 0.250. Okay, okay. Next pipe. That doesn't fit. So CB manhole 22 to blind connection 4. Circular 24. Sorry, CB manhole 22 to blind connection 4. It says 4571. We're at 4595. Close enough. 13. Upstream invert 177.22. Downstream 176.99. And the pipe diameter is 300. So there. Okay. Okay. So as I said, to enter the inverts and diameters and all the other data for the individual pipes, you can either do it like we did manually, like this, by clicking on each pipe, or we can use a table where we can change all the values in a table format and copy and paste and so on, so it makes it a little easier. So to do that, we're going to click the XP table list, and at the moment we don't have any tables created, so we're going to have to create a table. Now I want this to be a link table because I want to show all the pipes in it, so we're going to click on link tables, click add, name it whatever, I'll just name it link table, make it clear, click OK, and then we get this dialog box here. We need to select which type of information we want to have in that link table. and it is a little tedious. You have to find the right entries, and it's kind of hidden. So what I want is I want the upstream node name and the downstream node name. Click on it and say insert. Then the other ones would be located in conduit data. So I want the diameter, the length, a couple more things, and there's roughness I need. Upstream invert elevation, downstream invert elevation. I want the slope. Okay, now I want them in a specific order. So first I want the upstream node name. So I click on it and use this arrow to move it up. Then I want the downstream node name. Then I want the length, roughness, inlet elevation or upstream invert elevation, downstream invert elevation. I want the diameter, and then the slope. Hit OK, and you can do view, and it shows a table. So it shows all the links, upstream node, downstream, the length, which was calculated by the program, the roughness, which is by default 0.014. We changed some of them to 0.013, so now I want to change all of them, but instead of changing them one by one, we should be able to just Control C, highlight it, Control V, no, so right click on it and say paste. Okay, so now all the values are 0.013. We are going to set the upstream invert elevation and the downstream invert elevation from the table I have from the design drawings, and the diameter. There probably is a way to just copy and paste it from a spreadsheet, but for now I'm just going to do it manually. The conduit slope, we're going to leave it as zeros because there is another tool that calculates the slope based on the invert elevations and the lengths that we're going to put in now. So we'll start at the top, CB1 to CB manhole 8, 4322, which is about right. Roughness we have, upstream invert is 177.25, 8, downstream 176.82, and this pipe is CB9 to CB manhole 8, CB9, CB manhole 8, 2837 is the design, 2833 close enough. Upstream invert 177.25, downstream 176.97. The pipe size is 5. CB manhole 8 to manhole 7. 2779, 2776, that's fine. Stream invert 176.63, downstream 176.35, pipe size 300. Okay, so we're gonna close this for now. Open it again, and the values are there, and they should also reflect on the drawing itself. So we're going to find CB1 to CB manhole 8. So you can go here. No, I want to find object. So control, or we can just do Control F. CB1. So the pipe that we entered the information for was CB1 to CB manhole 8. We put that in the table. So if you right click on it, go edit, circular, those values are in automatically. So CB manhole 1, 177.25 upstream, 176.82 downstream. It's got the right size and the right Manning's N, and the length was calculated, so we know it's working. And we'll go back to the table and set all the other pipes. And the yellow actually means that it's showing the pipe that I highlighted in the plan view. So if I highlight CB9 to CB manhole 8, then it shows that that pipe is highlighted. Now just click elsewhere so that nothing's highlighted. Go back to the table and fix all the other values. Okay, so the table is pretty much populated except for one entry here, which actually is going to be an underground storage tank. So we're going to leave that for now, but we'll come back to it later. Save it, close it, and now we're going to use the slope tool. So we'll go to Tools, Calculate Conduit Slopes, select all, calculate, and it's going to calculate all the slopes based on the inverts and lengths that we put in. So now when we go back to the table, it has the conduit slopes populated. So at this point we can double check some of the values if we need to. We can also go back out and do a little bit of checking. So just want to see how the system is looking. So select a node, select downstream node, it sort of picks that branch, and up here dynamic long section, click on that, and it looks like it's kind of okay. Like there's nothing really weird about it. The pipes are pretty much matching obverts, except here maybe that's intended. Nothing's looking too much out of place. So that's a good start. We can close this one, check another one, so maybe from this point to the outlet. Pick that. So this whole branch is selected, and let's see how that looks. Okay, so looks okay except this location here. So we know that there's some problem at this point, so we can go back and check it. It is link 26 from manhole 3 to manhole 2. Manhole 3 to manhole 2. So it's over here. Let's see what the issue is. I'm just gonna select the shorter reach. Let's go from this point to that point. That's what the problem is. Okay, so there's something wrong with the pipe inverts. So we'll go back to this pipe, edit, and so it's manhole 3 to manhole 2. The pipe length is fine. Okay, here we go. So this one should be 175.51. This one's fine. That's okay. So we'll click okay. Now when we select that reach, up, not looking too much better. So it might be a design issue to check or something else. So we'll basically flag this and bring it to the designer's attention. What I'm going to do next is start setting up the subcatchments. So we're going to go to the runoff mode, We can turn on the catchments layer, and I believe there's a handy tool, calculate node, catchment areas, and this one will populate the area of each catchment based on the polygons that we drew. So it's all selected. I don't think we have to change anything. Here's the old area, which was 0 by default, and this is the calculated new area. So we're just going to click OK. And then we can check, for example, this catchment, click on it, right click, edit, and you can see that the area is populated. 2,190 square meters, which looks good according to my table that I received from the designer. So that is okay. So we're gonna start populating these tables, and we have one subcatchment for each per node, or the other way around. We have, for each node that's receiving runoff, we only have one one subcatchment. So we'll put in the imperviousness. So for this one, I know it's 100% impervious because it's a building roof, so we'll put 100. The width, I measured off the AutoCAD file, and that's the width of the subcatchment perpendicular to the direction of flow. So that's 19 meters, and the slope was given as 0%, but we're going to make this, we'll give it a little bit of slope, because I think even a roof has a little bit of, a flat roof has a bit of a slope on it. So we're going to give it 1%. Mark it here. Okay. So that's there. I think we have to click on the this box here next to number 1, so that this dialog box opens up, and here we are going to enter the rainfall gauge, which we haven't set up yet, and we will also enter the infiltration data, which we also have not set up yet. So I'm going to leave this for later. I'll just click OK for now, and OK on this, and we'll do the same thing with all the other catchments. So left click on this, right click, edit data. So this is a catchment contributing to CB54. So I go to my list from the CAD file, I find CB54. The list shows 0.06 for area, 0.062, that's close enough. The imperviousness is 0%, so I guess that's all grass. Okay, I hope that's correct. The width I measured as 12 meters. Slope I was giving as 6%. So, oh, sorry. Slope I was getting is 1.38%. Put that in like that. We can click OK. I guess we'll select this, go OK for now, and click OK. This one next. CP1 0.04 hectares. That's correct. Imperviousness is 25%. The width measured as 11. Slope 1%. The slope is entered in meters per meter, the width in meters, imperviousness is in percent, and area in hectares. See, I made a mistake in the slope information for this catchment here. I read off an incorrect value, so it's just CB 54.062 hectares. That's fine. Imperviousness is 0. Width is 12. The slope is 1.4%, so it should be 0.014. Okay, now we're good. Now, similar to what I did for the pipes, I'm going to set up a table for the catchments, so that we don't have to click on each one of them separately, and just can enter the data in table format. So we're going to go back to the XP table list. Okay, the pipes table pops up. We want to do a new table, so we'll go to XP table list. Now I already under nodes table I added a table, and I called it catchments. So basically I just went node tables, clicked add, typed catchments, and clicked OK. So I already added that one. So we're going to do oh, that's not right. Back to catchments. So okay, so we'll click on catchments and go edit. Alright, that's where I want to be. So so we will pick the runoff node, because we want to have the not the sort of structure information, not the CB manhole information, but the catchment area information. And we'll go to runoff node data. Okay, and we want to have the area, the width, impervious percentage, slope. Let's see which order I want to have it in. I want to have the area first, then I want to have the slope, then I want to have impervious percentage, and then the width. So that should be okay. We'll go on view. Okay, and now we have the table partially populated, so we can actually start adding the values. So let's see if we can do a 1 here. No, we can't. I guess we can't do a 1, so we'll have to do that manually. But we can populate the slopes. So CB9, I have the area as 0.07 in the table, that's fine. Slope is 0.01. Impervious percentage is 71%. And the width is 18. And I'm going to do the same thing with all the other subcatchments, and then I guess I'll have to go back and manually add the 1 into each catchment. The way to do that is I'm going to close this. So for example, here, left click, right click, edit data, and just click the 1, go OK for now. We'll set the parameters later and go OK. So back to the table, and we can populate all these other values. So CB manhole 8, CB 8. Let's see, where is that in the table? CB manhole. Okay, here we go. 0.09 area from the CAD file, which is 0.086 in the model. That's fine. Slope I have is 0.5%. Impervious percentage 78%. width 33. So we have that, and I think if we click on the node name and go to this button here, show object in network, and click on that, and it will pick that catchment area. So we can just left click, right click, edit data, and we can put that one there. Click OK. Go back to the tables. Okay, so that hasn't changed. Right, maybe it just needs to be refreshed. Okay, there we go. It's, the one is there. Continue to manhole 7. Okay. So what this tells me is that manhole 7 is, well, it's not receiving runoff because it's a manhole. So we'll see if we have that selected, and it's not on the runoff mode because it's a square as opposed to a circle, right? But for some reason it is still showing up in the table, so we're going to have to just ignore that. Okay, so I see the manholes are a little in green color, and the CBs and CB manholes are in black. So everything that's green, we're just going to ignore. Okay, so we'll go to CB manhole 6. CB manhole 6. Where is it? There we go. 0.17 in CAD. Oh, that's a little off here. 0.12. Well, that's what it is. Slope 0.005. Impervious percentage 88, and width 45. Okay, and I'm going to do this with the remainder of the catchments. Okay, so I have the whole subcatchment table populated pretty much. The only values that are not in are the manholes, which are not receiving runoff, and I'm missing a catch basin here, which I'm waiting for some data. So we're going to close this. Now what I want to do is I want to set up some global parameters. Specifically, I want to set up the type of soil or the infiltration rate that should be applied to each of these catchments. So I guess all of them except for the roof. So we're going to go see if we can find it. So configuration, global data, and we want to pick an infiltration. Name it something. If it varied per catchment, then we would name it according to the catchment, but here here it does not vary, or we're assuming that it's the same for each catchment, so we'll just say site soil add record. Okay, we're going to edit it. Okay, and here we can pick which infiltration method we want to use. For this application, we're using the Horton method, and we're going to put in values which are acceptable to the particular municipality, and those are 2.5 millimeter depression storage over impervious area, 7.5 millimeters for pervious. Manning's in, we'll put in 0.013 for impervious, 0.24 for pervious, and zero detention percentage. That's the percent of the subcatchment that's not where these detention values are not applied. I guess to be conservative, we can put a 25% value or more. I'm just going to leave it at 25 because that's what I've seen used before. So we'll just leave that as 25. Click OK and OK. And now for each of the subcatchments, left click, right click, edit. We're going to double click on number 1, and then for infiltration we're going to pick the site soil that we just entered, select, and it gets populated. Click OK. Okay, we'll do that for the next one. Left click, right click, edit, double click, pick site soil, select, and OK. And we'll figure out if there's a way to add that into the catchment table, and so this doesn't have to be done by one by one, but can be done in a table. Okay, I found where we can add that variable to the list, to the subcatchment table. So we'll go back to the subcatchment table, and I did that just by clicking on tables, and it sort of pops up because that's the last table that we viewed. So what I want to do is I want to add the soil type or soil reference to this table. So we'll go set up table variables, and things are kind of hard to find in here. So it should be under runoff node. I'd say runoff node data, subcatchment data. Okay, and here's infiltration reference. And while we're at it, we're going to add the rainfall reference because we'll be using that later. So we'll add infiltration and rainfall. We want to move it down. So rainfall. I want to have rainfall as the last value because we haven't put that in yet. So infiltration. Click OK. All right. So now we see that we now have the infiltration reference, and for the ones where we put the type of soil, it shows up, right? So I don't know what's okay. See before, yeah. So now we want to enter site soil. Let's see if we can just click on it. Yeah, you can just do this, or I guess there is a way of copying and pasting. Let's see. Yeah, okay. So these ones are okay. That doesn't work. Edit, paste. Okay, that works. Highlight these two. Right click, paste. That works. Yeah. Right click, paste. And these two, paste. Okay, so now we have the sites, have the infiltration set up for all the subcatchments. Now I also have it in. I have the site soil for the two roofs, and I guess it doesn't matter because it's 100% impervious, so it's not going to have any infiltration anyway. So we'll just put in site soil just so we have it populated. Save it. Let's just check if it reflected itself. So we'll go to this catchment. So that's this one. Left click, right click, edit, double click on one, and it has populated itself with the site soil. So that's good. All right. So now we are going to add some rainfall data. The way to do this is we go to global data in the database type, pick rainfall, and we will have 4 different storm events to model. We'll have a 100-year Chicago, 5-year Chicago distribution, 100-year SCS type 2, and something called a 150 millimeter stress test, which is basically the SCS type 2 storm plus 42 millimeters uniformly distributed over the 24 hours of rainfall data. So I think we'll start with the smallest event. So that's the 5-year 4-hour Chicago storm. And so I'm just going to copy this so we name it the same, and we'll also put the name of the storm here, Chicago 4-hour 5-year storm, add record, edit it. And what we're going to do is we'll have a constant time interval, because we know we have the data in 5-minute increments. Alright, so we'll click on that. Now we are inputting the rainfall as absolute depth, not cumulative. So we'll put absolute. Time interval we will have in minutes, and for this one it's 5 minutes, so we'll have 5-minute intervals. And for the rainfall inputs, I'm just going to copy the values in millimeters per hour into here, paste. Okay, and that should work. Let's see what that looks like. Something wrong. So okay, so we have to pick intensity here because we are doing millimeters per hour, right? So if we were entering the data in millimeters, we pick absolute depth. Since we're doing millimeters per hour, we pick intensity in millimeters per hour. Time interval is in minutes, 5 minutes. Look at the graph again. That doesn't look much better, but let's see if 8,000 millimeters per hour. So there's something fishy, because the maximum intensity should be like about 140. So we'll have to see what's happening. Intensity. Okay. We'll see what's happening. We'll come back to this. Okay, I can't figure out what the program is using to graph the rainfall data. When I select intensity, time interval in 5-minute increments, and I put in the rainfall input data in millimeters per hour, and I know that my maximum intensity is 140 millimeters per hour, the program graphs something that looks like the maximum intensity is over 8,000 millimeters per hour. So that's something wrong, and I tried different units like meters per hour and inches per hour, and it's just not doing what it should. So I have converted the millimeters per hour into millimeters in 5-minute increments. So we're going to put in the rainfall in absolute depth as opposed to intensity. So we'll delete this, select absolute depth, and we'll put in the rainfall data in millimeters. Insert, right click, paste. So now it's in millimeters, absolute depth, 5-minute intervals. Click on graph, and I'm getting 140 millimeters per hour, 140, which is what it should be, 139.575. So for some reason it's not graphing the rainfall increments correctly when I pick intensity, so we're going to just use absolute depth. And once we run the program, we'll make sure that the total rainfall matches the total rainfall that I calculated based on just adding up these rainfall values in millimeters. So that gives us the 4-hour 5-year Chicago storm. Next one we want to put in is the 100-year Chicago, so we'll copy the name. Put the new name here. Add, edit, constant time intervals. Here again we'll pick absolute depth. We'll check our rainfall increments are in 5 minutes, so minutes, 5. We'll copy rainfall data in millimeters. Here, graph it, and the maximum intensity is 220 millimeters per hour, which matches this here. So that's good. And it's 4 hours, 240 minutes, so about 4 hours. We'll double check that. Yes, so it's a 4-hour storm with the correct maximum intensity. So we'll okay. Next one we want to put in is this CS storm. Add record, edit, constant time. We'll put in absolute depth. Now this SCS is in 1-hour intervals, so we'll put in just put here hours. I'm just going to do 60 minutes, just so it's kind of consistent with the other rainfalls. Absolute depth. Put in paste. Graph it. The maximum intensity should be about 26 millimeters per hour. We look at that. Yeah, it's 2592, so that's correct. It's in 1 hour. Sorry, 24-hour storm, which corresponds to the number of minutes. Close it, close it, close it, and then the last one is the stress test. So we'll copy the name here, add record, edit, constant time. Again, we'll go absolute depth. Now this one is in 15 minute intervals, so 15. We'll use the actual rainfall depths. Paste. Check the maximum intensity. It's about 145 or so based on the graph. Go back. Maximum intensity 145. Check. So that's good. Okay, so now we have set up our storms. So now we have the model pretty much set up. I'm sure there's going to be some debugging needed and some corrections to be made. We will need to add some underground storage, configure the outlet and things like that, but basically we're getting close to having a running model. What we need to do next is set some job control parameters. So we go to configuration, job control, go to a runoff. We can set this later, the job title, things like that. We need to select global storms so that we don't have to set a storm for each catchment area. So we'll just do that, and it's asking us to enter the global storms here. So let's see how we do that. So these are the rainfall distributions that we put in. So we're going to click this one. We'll name it the same as the rainfall event for our 5-year. Return period is 5-year. We'll leave this as is. Click OK, and that's set up one of the storms. So now we need to do we need to do the other ones as well. So insert storm. We'll pick Chicago 4-year, 100-year. For our 100-year, 100-year storm. Okay. And we will add the other storms in the same manner. Okay, so we have all the storms entered. So we will go OK. Leave this checked. Next thing, we go back to configuration, job control, hydraulics, and let's see. So we're going to set some things here. It might have to come back and change it later, adjust it later if it doesn't work. So, but I looked at a previous project, and there the simulation tolerances were selected. So we'll just check it and leave it. Routing control was checked. We want to make sure we're using dynamic wave as opposed to kinematic. This method calculates solves the system using flow equations that allow for backwater and things like that, flow reversal, things like that. So we want to have the dynamic wave selected. And then the next one, we had junction default selected. We'll do that. We had the solve runoff and hydraulics mode simultaneously. We'll select that and save all results for review. We'll check that. Now we're going to have to come back and change the times. I'll have to see how that was done in the previous project. For now, we'll just click OK, and that's that. Okay, we're going to set a few more parameters to make the model run. So under configuration, job control, let's check the time control. So right now it's set to begin on the first day of the first month of 2020. We're going to leave that for now. We'll probably have to change it later to correspond to a flow curve at the outlet. But for now, we just want to make sure that these numbers match the numbers in job control runoff under time control. It does match. We're going to pick this use simulation start time for rainfall event because I had that in a previous project and it seemed to work. So we'll put that in. Click OK. Okay. Under configuration and interface files. This looks okay. So we'll leave it as is for now and we'll see what happens. I'm going to set some configuration parameters that I set in previous projects. Under configuration parameters, there's a whole list of parameters that can be set here. Like the only ones I've used before were something called min length, which is minimum length. So if you have pipes that are less than 10 meters, by default it's going to give an error. So I'm going to make the minimum pipe length for which an error will not be shown half a meter. So put that here, and then I don't remember what this one is for. I remember from a debugging exercise I was told by the support person to put this parameter in. So I'm going to put that in as well. I'm not really sure what it does, but I'm sure it had some kind of a purpose before. So I'll leave those in, press OK. Okay, I've been doing a little bit of debugging. There were some typos, some incorrect data. I also had to change the minimum pipe length that the program would consider, because it was giving me an error message saying that the pipe length is shorter than the minimum allowable of 10 meters. So I changed that by going into configuration parameters and changing the minimum length to half a meter. I probably could have made that 1 meter or so, but it doesn't matter. But then I've been getting this really weird message. Here's a solve button here. So when I click that, I've been getting a message saying a link has an undefined conduit shape. I contacted the support, and they really did not have an answer, and I think I figured it out. It's some kind of a bug in the program. For example, if I go to link 7, so Control F, link 7, find it. If I right click on it, edit data, and right now it's circular. So if I just change it to rectangular, click OK, and then go back and change it to circular, all the input parameter numbers are still in. Go OK and OK, save it and rerun it. That link is not there saying that it's undefined anymore, so that seems to have solved it. Next one is link 10. So Control F, find link 10, edit, change it to rectangular, okay, okay, go back, change it to circular, okay, save, run it, and link 10 is gone from the error, so I think that solved it. Now that we have the model pretty much set up, we are going to do a little bit of design. So first thing is we'll run the model, and I have selected a small storm to begin. That way, if there are any overflows or insufficient surface storage, it will not affect, or it should not affect this run, because most of the because the flow should really be within the pipes without any surface ponding. So we'll select the 5-year storm from this edit button here. Just click on the 5-year storm, run it, and we have no error messages, which is great. Okay, the error in continuities looks fine, everything looks good. So now we'll go to the outlet, and we know that the allowable release rate from the site is about 30 liters per second, which is pretty small. So we'll click on it and go to this button, review results, and as we can see, the maximum flow is about 150. So we need to reduce it down to 30. We're at 150, so that's way too high. So what we're going to do is we're going to add an orifice plate inside this manhole. The reason why we're not putting it in this manhole is because this branch drains mostly pervious areas, so the release rate from this branch should be pretty small. And if I actually click on it, it tells me that it actually flows into that pipe and then flows out. It's about it's about 10 liters per second. So we might have to revisit that later, because if it's 10 liters per second from this branch, then it might make sense to connect that pipe into this manhole and put the orifice here, and put storage in this like underground storage in this location. But for now, we'll keep that the way it is. We'll put an orifice plate at this location, and we'll have to put some storage at this location and see what happens. So let's just zoom in a little bit. So what we want to do is put an orifice plate here. Now the way to do this is we have to set up a dummy node. So we'll create a node, put it here for now. We'll call this orifice. Okay, and now this pipe now should connect to the orifice node, and we'll move it so it's here. Let's zoom in a little bit more. Move that just as close as possible to the manhole itself. There we go. Okay, and then to model the orifice, we have to set up something called a multi-link. So we'll click on the multi-link here, click there and there, escape, and that sets up a multi-link. Now this pipe now it has to be adjusted. Let's see what we have there. Well, it's still okay. It's the invert. Like the inverts are still correct. Let's just double check that. This is pipe going to manhole 2, from manhole 3 to manhole 2. Manhole 3 to manhole 2. Where is this? So 175.81 upstream, 175.77. Just going to highlight that here. It's a 300mm pipe, and we'll keep the length because it should, even though we moved that upstream node, it's still the same pipe, so we'll just keep it at 8 meters. Okay, and now for this multi-link, right click on it, edit data, and the instructions I got from support is that add the dummy node, which we did. Make the link between the node and the dummy node a multi-link. Within the multi-link, you will only select the orifice option. Make sure that the conduits are unchecked. So conduit is unchecked. We'll select just an orifice. Okay, and now it's not a bottom outlet, it's a side outlet, meaning that it's draining. It's going. The orifice is on the side of the manhole. We're just going to call it orifice because we only have one. If we had more, we would call them orifice 1, orifice 2, and so on. Now the orifice area, we'll use the calculate button. It's a circular area, and we're going to guess the orifice size. It's in meters, so I'm guessing it's going to be 100mm orifice. So let's put 0.1 meter. So 100mm orifice. We'll go OK, and it calculates the area in square meters. Typical value discharge coefficient is 0.62. And we need to set the orifice elevation. So the orifice elevation equals the upstream invert of this pipe, which we just checked, and it's 175.81. And hit OK. And it says the top of the orifice cannot be higher than spill crest elevation. Okay, so we're going to have to do a little bit of investigating to see why we are getting this error. Okay, the reason why we are getting that error message is because we have not set the inverts at this dummy node. So we'll go edit data. The invert elevation is it matches the elevation of the orifice, which we said was 175.81, and the spill crest is the same value as the spill crest we assigned for manhole 3, which was 179.15. 915. Okay, and we'll go back to the orifice. And we gotta do this again. Set 100 millimeters, circular, 0.62, side outlet, 175.81, and hopefully this will work. Okay, the orifice is already used by another node, so we'll call it this orifice plate. Okay, that worked fine. I think I'm going to rename this into orifice node. Okay, we'll save it and see if it still runs. Okay, so we're getting an error message. Orifice node, no subcatchments are selected. Okay, that's an easy one. So the reason for that is because you have to go to the runoff mode and delete the orifice node from the runoff, because it's not getting any direct runoff into it from a subcatchment. So we'll just go press the minus sign, save, and run it again. Okay, great, no errors. Okay, so now we'll go back to our outlet and see if we are getting any closer to our 30 liters per second, and we are at 47. Great. So what I think we can do here, I think it's, I don't think it's this node here, this pipe, that should be connected back to manhole 3 as opposed to going to manhole 2, because the flow we're getting through the orifice, oops, is 43. Okay, well, maybe not. So we're getting 43, and this is kind of might be irrelevant. It's, hold on. So through this pipe we are getting 4 liters per second. Okay, so that's pretty low. 4 liters per second. Here we're getting 43, and the combined flow is 47. So it's, yeah, so it's kind of minor. So we need to have a smaller orifice. Okay, so let's make it a 90 millimeter. .09. Save. Solve. Okay. Let's see what we're getting for an outflow. 39, 40. Okay, so we'll need to do something to get the flow down even more. So what I'm going to do, instead of reducing the orifice size even further, what is happening there is that there's because of the restriction, the water level in the pipe is pretty high, and it is creating a lot of head on the orifice. See, like the head acting on the orifice is pretty high. So if we put a storage here, then we should be able to reduce that head by containing the flow within that storage, and because of the lower head there will be less outflow. So I think we need to put in a storage node at this location here, and the way we're going to do that is we're going to add a node, put it here for now. We're going to name it stormwater management tank. Okay. This pipe, we'll make it go into this tank, and we'll have to add another pipe from here to there. Okay, we'll just line this up so it's a straight line. Okay, good enough. Now this will be a storage node, and we're going to set up the parameters for that. So we have to fix just the elevations in for the tank, right, for these two pipes. So let's see. I'm going to do that and then come back and show it. Okay, so after putting in this swim tank, stormwater management tank, XPSWM keeps crashing on me. That's the problem with this program. Sometimes it just, if it doesn't like something, it just keeps crashing, doesn't tell you what the problem is, and it takes a long time to debug. And there's not much you can do to figure out exactly what it is, so just keep trying something different. So what I'm going to do is I'm going to delete this stormwater tank, and I will model the storage using sort of like a box shaped conduit. We'll see if that works. So what I'm going to do is I'll delete this pipe. We'll delete the tank. We'll reconnect this manhole with that one. Okay, and we have to specify the correct inverts. So we'll keep, well, okay, we'll keep it. All right, so we'll go with rectangular shape. So we'll let the program calculate the width. We'll put in 0.013, so sorry, the length. We'll put in 0.013 for Mannings. We're just going to start with a 1x1 box culvert, and these inverts they should match manhole. Let's see, the outlet at manhole 20 is 176.84, and I believe the inlet to manhole 3 is 176.81. We'll put that in. 81. Okay, we're going to go tools, calculate slopes. Tools, calculate lengths. Okay, so now those values should be populated. Yeah, so we have the length, and we have, and the slope is calculated somewhere else, but okay. Also, I want to make this 81. All right, let's see if that works. Okay, so that seems to have solved the problem with the storage crashing. All right, so let's see what we are getting for the flow. We wanted to have maximum of 30 liters per second, and we are at 40. So let's see what's happening at this culvert, at this storage now. So it is getting filled up. It's hard to say here. 177. Looks like it's getting filled up by 2 meters. So let's see what's happening in profile view. Well, it is pretty full, so we need more storage basically. So we'll make this. Let's exaggerate. Let's make this. Let's keep the height at 1.5 meters. We'll make this 3 meters. So that'll give us 3 times 1.5 times 22.25. It's about 100 cubic meters of storage. I think we need, from a previous design, I think we need about 300. So we'll go 300 divided by 22.25 divided by 1.5. Okay, so that's 9 meters. So let's put in a 9 meter wide pipe. Okay, it's taking a little bit longer to calculate. And we'll see what's happening in profile view. Well, I'm not sure if it's any lower. It's our flow. Not going down much. Okay, so we're gonna have to do some adjustments and hope that we can figure this out. So since I am using a rectangular conduit, I went to the tables and I added something called bottom width, and by doing that it looks like it is now showing it's showing the width of that rectangular conduit that I modeled. Now I think I want the slope to be moved over, so I'm going to go back, move the slope down one. Okay, that's better. So for this rectangular storage chamber that we were modeling, I currently have a 1 meter height and 15 meter width. So we can save it. Oh, I don't know what that is. That's a problem. Okay. Another thing is under view. If you click quick data view, show or hide, it's a little bit easier to change the size of the pipe. So here there's that 15. If I want to change this to 16, it's easier to do it like this. Okay, let's see if it's running. Okay, it seems okay. So what I have done is I have reduced the height to 1 meter, and I'm adjusting the width so that the hydraulic grade line is within the chamber. So now see it's still way up. So I'm going to go, I'll put in like 20 meters. Run it. I want to get that hydraulic grade line within the chamber itself, so that the head is reduced, and therefore the flow through the orifice is reduced. So we'll plot it from here to here. Okay, it's within the chamber, so I'll leave it like that for now. And what's it giving in terms of flow? 29. So we're good. So I think we're going to leave it at that. Well, let's see what happens if we run it with the 100-year, because that's what's going to drive this design. So we'll go to Chicago 100-year. Okay, run it. And I expect the HGL to be higher. Actually, it's good if it's higher, because we want the surface storage utilized. So it is higher. Now the only question is, what's our release rate? Oops, 54. So that's not good. So we're going to have to reduce the orifice size, because our maximum was 30. So we're going to have to keep adjusting this until we get the release rate correct. So what we are going to do to try to fix the 100-year flow scenario is, for the outfall, we actually have a backwater graph corresponding to a 100-year 4-hour Chicago storm. I have the graph is here. This is the backwater, and this is the storm event. So it lines up pretty well. So we're going to put in this curve to the outlet. Here it is. Here's the curve. It's in 5-minute time intervals, which is the same as the storm event. So we're going to put that in. So the way to do it is we go to the outfall, edit data, go to the outfall, and go to user stage history. Click on coordinates, and we're going to paste this here. Hopefully it works. Okay, graph it. So it's a 16-hour duration. So that's okay. It's 15.833, so close enough. The maximum is 178.72, so that also looks good. So there it is. I'm just not sure what's going to happen since the maximum AGL is actually higher than the top of the manhole at which it was measured. So let's see, let's see if the program gives an error. Okay, what's there? Okay, we'll save it. Try to run it. Oh, looks good. So let's see what the release rate is. It was like I think around 50 last time. Alright. Okay, So it looks like it's actually flowing into the site first before it flows out. Program doesn't give the maximum flow value because it's giving the maximum negative flow value, so you kind of gotta do it. You have to estimate what the number is. So this is 20, 10, 20, 30. So it's pretty close. What is it over here? Same thing. So we don't know what this number is, so we'll have to somehow get that from the output, I guess. Yeah, I need to know this value here. But the maximum flow, it gives actually this value, not this one. This being the maximum negative value. So we'll have to figure it out. We'll have to get to see if we can get a table of values as opposed to a graph. Don't know how to do it at the moment, but we'll have to figure it out. What I'm doing now is setting all the manholes and storm plugs and blind connections to be sealed so that there's no water escaping from the system at those points. So I already have this manhole 7 is sealed. I did the same thing at the outfall. Let's see what else. It should be sealed. Blind connection. This manhole. Manhole. This one. This one. Sealed. Okay, see if it still runs. Yeah. Okay, we also need to seal the other. A couple more manholes here. Sealed. Should be sealed. I believe the outfall already is. Good. We'll rerun it. We can zoom out and click this dynamic plan view and see if we have any ponding happening. See any little waves. That's a good sign. Let's try that again. Oops. Some red nodes, whatever that means. It's kind of hard to tell. So let's go back to this view here. It's okay that the AGL is above. This is a manhole, so it just means that there's pressure in the manhole. And actually, the brown line it's something called a spill crest. So that's not the top of the CB. That's where the CB would spill. So that's the maximum allowable ponding elevation, which unfortunately the profile is not showing this too well, because this, for the manhole, this elevation is the actual top of the manhole, whereas the CB, that's the top of the CB plus the 0.3 or whatever allowable ponding depth. So it's just the way the program displays it is not very very good. Anyway, so this profile looks pretty good. There's no little waves showing ponding. This one, also good. You can check. Ooh, what's happening here? Oh, some pressure, but no water spilling out. That's the roof connection. Okay, that's fine. So we can reduce our storage a little bit, I think. Our underground storage. Yeah, below surface. Let's do this. Yeah, that's fine. So check the CBs like this. CB floor, our maximum ponding is 179.55. So we're way below that. In fact, there's not much ponding happening. What about these ones? CB5 allowable is 179.55. We're at 179.40. There's some ponding, but not that much. So we'll just have to optimize the system to utilize all the surface storage it can, and without going over with the underground storage size. There's a problem with the way the program is set up now. When I run the 100-year storm and I want to check for the flow rate, which we have a 30 liter per second allowable release rate, it doesn't let me do it because there's some flow into the system. Sorry, I already made that change, so I'm gonna remove it. Well, now it seems to be okay. Oops. But I added a tidal gate, or when I ran the program for the first time, I had this. I did not have this checked. So when that happens, I just have to save it. It shows reverse flow into the system, which is not what we want, because then we can't see what the flow rate out of the system is. Let's see if this will work. Well, for some reason, it's showing the results with the tidal gate in. I don't know why, because it's not set. But the way I fixed it is I went here and I clicked tidal gate, pressed OK, and ran it. And it seems like when I uncheck it, it still has the tidal gate applied to it. So this way we can check the release rate, and it is 30 liters per second, which is what our target is, so that's good. I'm going to set up another table for the nodes, because we set up a table for the links, catchments, but nothing for the nodes. So I'm going to go under nodes, and I'll go add, call the node table, and the one I have there is not the runoff information, but the hydraulics information. Let's see what's under here. Hydraulics. So we'll put in data, storage node data. Right, so we want to have storage node data, node surcharge. What I want to show is the maximum ponding elevation. It's such a frequently used parameter, and it's possible to find. Calculated depth, storage node data, ponding type, initial depth, invert elevation. Okay, I don't see it. Okay, so let's see what's here. Maximum water elevation. Okay, let's put that in. Maximum. Let's also put maximum water depth. There's nothing. This would be for the catchment. So let's do this. Depth and elevation. Okay, we want to view it. Alright, so not too bad. So let's check it. So let's go CB1. It says 178,978. So we'll go to CB1. 178,978. Okay, so that is what I need. Good. So now I don't think there's any way to check for the maximum ponding depth. You gotta export that into a spreadsheet and then calculate it based on the rim elevation. So I'm going to do that separately. So here we are about 1 day later. The storage node I couldn't get to work was actually a bug in the program, so I have an updated version of XPSTORM 2019.1.3, and I just ran it on a test file and it seems to work. So we're going to go back and replace this huge pipe with an actual storage node. So I'm just going to get rid of this pipe, pick a new node right here. I'm going to remember to go to the runoff node and subtract it. Okay, so we'll connect it from this manhole to this one. Now this will be a storage node. We're going to give it I'm going to try 400 cubic meters so at 1 meter depth. So 0.045. So that's 45 times 10,000. So that's a 450 square meter footprint times 1 meter depth. That's 450 cubic meters. Put it in that way. I'm going to call it a sealed node, meaning that it should not overflow at this point. In the inverse elevations, let's see what that was. 176.84, so we'll make this 176.82. The top of this manhole was at 179.37, so we're going to copy that to this one. Might adjust it later, but for now we'll put it like that. Okay, this one is going to be at 375. I forgot the number again, so let's see what that was. 176.84. This was 176.82 if I remember correctly. 84, 82. We'll make this a 1 meter long pipe because it's not, because the storage will be from the manhole to the manhole, so we'll give it a 1 meter length. Two, 76.81, 5, 1 meter long, 13 Mannings. Okay, and the node is swim tank. Okay, save. See if it works. Continue. Well, I'd like to see the warning messages. What is the warning message? So would you like to continue? Yes. Oh, what is the warning message? Conduit depth less than recommended minimum. So I think I have a typo there somewhere. Link 35. Which one's link 35? Oh. Okay. Okay. Add an extra 0. Save it. Hopefully no. Okay, good. No error message. Okay. Let's see what our release rate is. We're okay. We're close. We'll have to adjust it a bit, but we're at 32 liters and our target is 30.1, so we're close. So we'll have to figure out what to do to optimize the system a bit. Okay, I'm going to set up a few things here that make the viewing of the results a little bit easier. So one of them is I don't want to have to select the pipes every time I want to look at the results. So I'm going to select this reach, and we'll go under view, save view, and we will call this reach 1, can rename it later if we need to. And we'll call this reach 2. Call this reach 3. And to switch between these views, just go to restore views. There's reach 1, reach 2, reach 3. So that when, let's run 100-year storm. If you want to see the reach 1 results, just go reach 1, click here. If you want to see the other ones, we just select the reach, and there we go. Makes it a bit easier. Next thing I'm going to do is we have a number of different boundary conditions. For the 5-year storm, there's no tailwater. For the 100-year storm, 4-hour, there's a 4-hour tailwater graph, and for the 24-hour, there's another one. So I'm going to set up a number of scenarios. So we'll go under Edit. Under Base Scenario, we'll say New. We'll call this the no tailwater. We'll have a 100-year 4-hour tailwater. We'll have a 100-year 24-hour tailwater. Okay, so now we already have the first two in the model, so I'm going to select this one. This is the 4-hour tailwater. Go to the outfall, make sure that that's what's in here. Graph it. This is the tailwater corresponding to the to the 4-hour storm. So that's correct. Okay, save it. Let's do this again. I think I should be selecting here no tailwater. Sorry, 100-year 4-hour tailwater. Go to this, edit it. It's fine. Okay, and then go to the no tailwater scenario. And for that, oops, I didn't want to do this. And for this one, I wanted to go to the outfall and picked the free outfall option. Okay, so now when we select 4-hour tailwater, it should have the graph in it. And when we select no tailwater, it should have the free fall. Now there's another condition that we have. It's a 24-hour tailwater conditions. So that's this one. So we're going to add that for the 24-hour tailwater. So first we'll delete everything. Insert. Copy the data. Graph. So that's the 24-hour tailwater condition. So that should be fine. Okay. 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 Now when we run the program, we have to remember to select the correct tailwater. So if we go under no tailwater, just double check this. It's free outfall. If we go under 4-hour tailwater, oops, what happened here? Something went wrong. I don't know what happened here, but this row shouldn't be there. Looks fine. Don't know how that happened. So let's try this again. So no tailwater, free flow condition, 4-hour tailwater. That's the correct one. Go to the 24-hour tailwater. You should get the longer graph, so that's fine. The 24-hour tailwater is actually the 4-hour. It's just shifted in time so that the peak matches the peak of the 24-hour storm. We were not provided with the 24-hour backwater graph, so we just used the 4-hour, shifted it in time so that the peak corresponds to the peak of the 24-hour storm. Good. We have some adjustments to be made. One of them is for the Horton infiltration method. I want to change the parameters per the city guidelines. So we'll go to configuration, global data, infiltration, pick the one that we already entered before, edit. We are in the method selection dialog box, so we'll go on Horton, and the parameters that the city wants us to use for soil type C would be 50 for the maximum infiltration rate. We will not put in this dry one, that just seems too high. So we'll put in the maximum, we'll put according to the normal conditions, 50. The minimum infiltration for loam soil is 2.5. So instead of 10, we'll put 2.5. The decay rate, that's this in 1 per hour in 1 per hour units, and the input is 1 per second. So I believe that's the correct conversion. The maximum infiltration volume, that's just if it's 0, then it's ignored. So we'll keep that as 0 because we don't want to limit the infiltration volume. So we'll click OK. Save. Let's just make sure that it runs. Yeah, that's okay. Good. when I was sizing the underground storage, I sized it based on whether or not there was overflow at the individual catch basins. To optimize the sizing, we can actually let the catch basin spill from one catchment area to the other. That way, if there is extra capacity in the adjacent catchment, then the catch basin will spill and it will not overflow. Overflow meaning that the model does not account for that runoff anymore, and it's just not a good condition to have in the model. It just kind of signifies an error. So I'm going to set up overflows between the individual catch basins, and I have been provided with the spill elevations. Hopefully they correspond to the top of the ponding elevation. We're going to double check that, but the way I'm going to do it is if there already is a connection between two catch basins, then we will turn that into a multi-link. That way we can have the pipe as one part of the link and the weir as the second part. If there isn't a connection already, we'll just set up a multi-link anyway, and we'll just select the weir part. Okay, so the first one, we have overflow from CB5 to CB manhole 22. So we're going to find CB5. It's over here. And we're going to turn off the catchment layer for now, so it's easier to see. Okay, so we have overflow from CB5 to CB manhole 22. So we'll click on this, turn it into a multi-link, edit it. So the conduit is still there. That's what we put in before, which is the 250mm pipe. So that's fine. We can leave that as is. So now we'll have to put in the weir, and the name of this weir will be CB5 CB manhole 22. The crown elevation is let's see, so the crown, okay, so the crest is where it starts overflowing, so crest, crown. So for the crest, we'll put the spill point, which is 179.55, and for the crown, we are just going to put in let's say 0.50 meter depth. So we'll make that for now and see if the overflow depth is exceeded. So we'll put in 179.70. So that's the crown minus the crest is 0.15. And that should be it. See if that runs. Nope. Okay. So we need to put in some more parameters there. Weir length is 0. So where do we put in the weir length? Oh, weir length. Okay. But what I'm missing here is the weir width. Maybe the length is the actual length of the width of the weir. Okay. We'll put in 10 meters just to start. Let's see if that runs. Okay, it runs. And at the moment there shouldn't be any overflows because we sized the storage so that we don't exceed those maximum ponding elevations. Yeah, so our rear is at this elevation, it never gets there. Alright, I'm going to check a few things and come back. Okay, let's look at these input parameters again. We'll select the weir. Here, the weir length is actually the width of the weir, right? So we're just going to estimate that at 10 meters. This is fine. This is okay. The discharge coefficient 1.7 is okay. 1.64 is the typical value for a broad crested weir, so we'll leave that as 1.7, the default value, and that should be it for input. So again, CB5 to CB manhole 22, we have overflow at 179.55. We'll give it 0.50 meter allowable depth, and we'll leave it at that. Okay, next one we have CB manhole 22 to CB4. This one. So here, since we don't have a connection model between the CBs, between storage areas, we are going to have to put in a new one. So we'll go from the CB to the CB with a multi-link. We're just going to set up a weir. Call it CB manhole 22 underscore CB4. The spill crest is 179.55, and we'll give it 15 centimeters of allowable depth, so 179.70. Leave the discharge coefficient as is. We're put in 10 meters for now. Next, we have CB4 to CB3. I believe that's this one. CB3, yes. Here's the previous. Here's the previous view. Okay, here's the previous view button. So we'll connect these two CBs. Right click, edit data, weir, 10 meters, name CB4, CB3, 179.55. These spill crests are all the same elevation. 70. I don't know if we'll have to give it a name. Oops, we need to do that. We need to put that node in. We'll save it and see if we have to name those. No. Okay. CB3 to CB 20. Well, I don't really want to go to CB manhole 20, which is the designer gave me, so we'll change that. We want to make the connections between CVs and not between manhole. Okay, my red pen. this will be not CB3 to manhole 20. This is going to be CB manhole 4. We'll set that up as a separate multi-link. Right click, edit data, here, 10 meters, CB4 to CB manhole 4, 17955, 17970. We have that overflow. CB54. Okay, my list is not accurate, so I'm going to have to investigate and get back to this. It's fine. So next one is CB54 to CB manhole 11. We're going to turn this into a multi-link because we already have a link. The multi-link, edit data, add a weir, give it 10 meters. CB54 to CB manhole 11. What's the spill crest here? So this one's lower, it's at 179.05. So we'll make this one 179.20. Give it the 15 centimeters of ponding. Okay, next one we have on the list is CB manhole 11. CB manhole 10. So that's this one. Turn it into a multi-link. Here. And here. Meters. One 79.05. 179.20. Yeah. And save it and continue with all the other ones. Here we have an error. We have CB54 spilling to CB1 area or vice versa. But this one here, CB1 is not spilling to CB manhole 8 but to CB manhole 9. So we are going to change this back to a single link. Hopefully the pipe data is still there. It looks like it's okay. But instead we're going to put in a multi-link. Two CBs, so CB1 to CB9. These two. CB1, CB9. 5, 20. Okay. So this one spills there, this one spills there, this one spills here. The next one is CB manhole 8 to CB manhole 6. 8. Okay. So the model is pretty much set up. We have added weirs between catchment areas so that if the water level exceeds the spill point, it spills to the next catchment and so on. We're going to run the model with the highest storm that we have to model. So we were doing the 5-year 4-hour, the 100-year 4-hour Chicago, and the 100-year 24-hour SCS Type 2, and as well as a 150 millimeter stress test, which is basically the Chicago storm with an additional 42 millimeters distributed over the duration of the storm. So we have that set up. Run it. No check that the model is working properly, we can go to this icon here, go dynamic plan view, and we run it, and if we don't see little waves on any of the CB manholes and CBs, that means all the flow is contained within the model. There's no flow lost out of the system, and everything's being accounted for. So looks like it's running fine. There's something called flooding, but it just means that it's overflowing to the next CB. So we have no outflow no overflow from the system. That looks fine. We can check a few CBs. For example, this one. It looks like 179 is the spill point, so it is spilling to the next CB. 179.053. So those about 5 centimeters of overflow. It is within the site boundary, site grading. It's not spilling out of the site, so that's good. We can go to the tables and we'll see what the actual maximum water elevation is. One way, the only way I'm checking for the ponding depths is pasting these water levels into a spreadsheet and basically just subtracting the rim elevation from the maximum water level and checking to make sure that it's within the acceptable ponding limit, which is 0.3 of a meter. So that ended up working fine. We can also go to the outlet. I set up some views here for quicker viewing, so we can go to the outlet, check for the flow rate. 32 liters per second. It's okay. The 30 liters per second is the allowable, but this should be acceptable for this stress test. Running the 100-year storm results in peak flows less than 30 liters per second, so that's fine as well. So that's one thing to check. There's a previous view. So the model is pretty much completed. We have only one orifice in the system at this location. Oops, that's not what I wanted to click on. Zoom in a little bit more. So there's the orifice. Unfortunately, the program doesn't keep track of the orifice size. It only calculates the area based on the orifice. So we know that it's 0.005 divided by pi, square root of that, times 2000. So that's an 80 millimeter orifice plate in diameter. So that's working fine. I ran a couple scenarios with rooftop storage. However, that's not the model that we're presenting. So this one does not have rooftop storage. But I did add it for these two buildings. It made a little bit of a difference, but not as much as we were hoping for. So we reverted back to the model without rooftop storage, with just one underground storage tank, an orifice plate, and it's working fine. So this is our model. That basically takes care of the project for the time being, unless there are changes, and that's it.